Good morning, students. Today we begin one of the most important chapters in physics, how forces affect motion. Have you ever wondered why a stationary football suddenly starts moving when someone kicks it? What makes objects speed up, slow down, stop, or even lies in a powerful idea called force? Let's discover how forces control almost every movement we see around us.
Students, let's imagine a fascinating world where friction suddenly vanishes. Without friction between our shoes and the ground, we would be unable to walk. Vehicles would lose traction because their tires could no longer grip the road. Objects that start moving would continue moving for a very long time because nothing would slow them down. Although friction opposes motion, it is one of the most useful forces in our everyday lives.
Before release, balanced. Before you let go, the coin stack sits still. That stillness tells us the forces on it are balanced. Nothing is winning yet. On release, net force. The instant you release, the rubber band flings the coins forward, beating friction. There's now a net force forward, so the coins speed up. They accelerate from rest. After losing contact. Once the coins leave the rubber band, no one is pushing them forward anymore. Only friction remains, quietly dragging backward, so the coins slow down and finally rest. Friction always has the last word. Different surfaces, different friction. Same push every time, yet different distances on different surfaces. What a clue! It proves each surface offers a different amount of friction. That's the whole point of our experiment. Materials. In the last activity we saw friction. Now let's actually measure it. All we need is a spring balance and a wooden block. Let's turn detective and put a number on friction. Setup. Lay the spring balance flat, check that it reads 0, and hook the wooden block to it. Now we're ready to pull and read. Pull and read. Pull slowly, gently increasing your force, and keep your eye on the scale. The very moment the block begins to move, note that reading. That number is telling us something important about friction. Constant velocity means, if you can pull so the block moves at a steady speed, the net force must be 0. That means your pull exactly matches friction, so the balance reading is the friction force. Clever, isn't it? Compare surfaces. Repeat on all your surfaces and line up the readings. Do you see it? The surface where the coins traveled farthest gives the smallest reading. The two experiments agree with each other beautifully. Reading equals friction. So the spring balance is really a friction meter. A big reading means strong friction. A small reading means weak friction. Now we can measure what we could only feel before. Combined conclusion. Put both activities together, and here's our grand conclusion. Less friction means the object slows down more gently and travels farther. Simple, powerful, and something you proved with your own hands. Think as a scientist. Thought experiment. Now let's think like scientists. Imagine a surface so perfectly smooth that friction is 0. Would the coins ever slow down? Or would they glide on forever? We can't build such a surface, but our minds can. This is called a thought experiment. Meet a scientist, Galileo. Long ago, the brilliant Galileo imagined exactly this. He reasoned that if you removed every obstacle, a moving body would keep going forever on its own. No one had thought that way before, a truly revolutionary idea. Meet a scientist, Newton and inertia. Isaac Newton took Galileo's idea further. He named objects' laziness to change their state, inertia, and in 1687 gave us his famous 3 laws. We honor him with the unit of force, the Newton. What a legacy! Statement. Here it is, Newton's first law. A resting object stays lazily at rest, and a moving object keeps moving straight and steady unless some net force disturbs it. Objects simply love to keep doing what they're already doing. 0 net force. So if the net force is 0, nothing changes. No starting, no stopping, no turning. 0 net force means 0 acceleration. No push, no change. Remember that pairing. Note on constant velocity. Be careful with words here. At rest just means 0 velocity. Constant velocity means the speed and the direction stay unchanged, moving straight at the same pace. Rest is really just constant velocity that happens to be 0. Example 6.2. Suppose you push a box exactly as hard as friction pushes back. The two cancel, net force is 0. So by the first law, the box keeps gliding at a steady speed. It won't speed up or slow down, just cruise along. Example 6.3. No net force graphs. When there's no net force, only two peaceful situations are possible. The object sits still, or it moves at a constant velocity. Let's draw both on graphs so you can recognize them at a glance. Graphs for rest. For an object at rest, its position never changes, so the position time graph is a flat horizontal line. And since velocity is zero throughout, the velocity time graph sits right on the zero line. Graphs for constant velocity. For steady motion, the position keeps increasing evenly, a slanting straight line, and velocity stays the same, so its graph is a flat line above zero. Neat, straight lines everywhere. That's the signature of no net force. Note: friction-free case. Here's the deep truth the first law reveals. Force is not needed to keep something moving, only to start, change, or stop it. On our real floors, we keep pushing only because friction keeps stealing the motion. Pause and ponder. Constant velocity. Quick question for you. A car moving at a constant velocity, is there any net force on it? Think about the first law before answering. Hint: constant velocity means no change. Pause and ponder. Possible situations. With zero net force, which of these can happen? Resting, constant velocity, or constant acceleration? Rule out the impossible one. Remember, acceleration always needs a net force. Pause and ponder. Zero net force by design. In real life, forces are everywhere, yet we can still arrange them to cancel to zero. Can you think of an example? A book resting on a table is a lovely one. Gravity down, table pushing up, perfectly balanced. Transition to second law. The first law told us what happens with no net force. Naturally, we now ask, and what if there is a net force? What exactly does it do to the motion? That's the beautiful question the second law answers. Force produces acceleration. A net force changes an object's velocity, and any change in velocity is acceleration. So we can say it simply: force produces acceleration. Where there's a net force, there's acceleration. The key question: but how much acceleration? Is it more force, more acceleration? Does the object's mass matter? These are the exact questions we'll now pin down with experiments. Think as a scientist. First hypothesis. From everyday life, you already sense it. A gentle tap moves a ball slowly, a hard kick sends it flying. So our first hypothesis: for the same object, more force gives more acceleration. Let's test this guess like real scientists. Using weights for forces. How do we apply neat, known forces? Clever idea. Use weights. Since the Earth pulls each weight with a known force, hanging different weights lets us apply different, steady forces. Gravity becomes our tool. Materials. Time to build our own little cart and pulley machine. Gather wheels, pencils, a cardboard box, a paper cup, a small pipe as a pulley, thread, some coins, and a weighing scale. It's like a mini science project. Build the cart. Push the pencils through the box as axles, fix a wheel on each end, and tie a thread to the front. There's your cart, ready to be pulled and studied. Pulley setup. Run the thread over the pipe at the table's edge and hang a cup on the other end. As the cup falls, gravity pulls it down, and through the thread it pulls the cart forward with a steady force. Beautiful arrangement. Measure the cup mass. Before releasing, weigh the cup and whatever's inside. We need to know our masses precisely. Good scientists always measure carefully. Record time, T1. Let the cart go and film it in slow motion on your phone. From the video, measure how long it took to cross the table. Call that time T1. Slow motion helps us catch tiny time differences. Double the force, record T2. Now double the mass in the cup. That doubles the pulling force. Run it again and record the new time, T2. Same cart, bigger force. Let's see what changes. Kinematic analysis. A little maths now. Both times the cart starts from rest and covers the same distance. So the distance equals 1/2 times acceleration times time squared for each. Setting them equal gives the ratio of the first acceleration to the second equal to t2 squared over t1 squared. Don't be scared of the formula, it's just comparing the two runs fairly. Conclusion. Force. Plug in your times and you'll see it plainly. With the bigger force, the acceleration grew. So for the same cart, more force means more acceleration. Our first hypothesis stands proven. Think as a scientist. Second hypothesis. Now a second guess. You know it's easier to push an empty trolley than a loaded one. So for the same force, a heavier object should accelerate less. Let's test this too. Vary the mass. Same setup as before, but flip the change. Keep the pulling cup the same, and this time double the cart's mass by loading it up. Same force, heavier cart. Measure and compare. Weigh the loaded cart, run the experiment, and compare the accelerations of the light and heavy cart. The numbers will tell the story. Conclusion. Mass. And there it is. The heavier cart accelerated less. So for a fixed force, acceleration goes down as mass goes up. They are inversely related. Second hypothesis proven. Statement of second law. Let's crown these two results into Newton's second law. A net force accelerates an object in its own direction, with acceleration increasing with force and decreasing with mass. One law captures both experiments. Formula: A equals F over m. In the language of maths, that's simply A equals F over m. Force on top makes acceleration bigger. Mass at the bottom makes it smaller. The whole law fits in 3 letters. Formula: F equals ma. Rearrange it and you get the famous F equals ma. The equation you'll use again and again. Memorize it. Love it. It's one of the most useful formulas in all of science. Defining 1 Newton. Now let's define our unit using this formula. Take 1 kilogram and give it an acceleration of 1 meter per second squared. The force needed is 1 kilogram times 1 meter per second squared, which is 1 Newton. That's where the unit comes from. Definition of 1 Newton. So say it clearly. 1 Newton is the force that gives a 1 kilogram object an acceleration of 1 meter per second squared. A tidy, exact definition. Remember it for your exam. Acceleration due to gravity. When anything falls, the Earth's pull gives it a special acceleration we call g. Its unit is meter per second squared, just like any acceleration. Every falling object shares this same g. Weight formula. F equals mg. Put g into F equals ma and you get F equals mg. That's the weight of an object. So weight is just mass times g. This little formula connects mass and the force of gravity. Value of g. Near the Earth's surface, g is about 9.8 meters per second squared. For quick mental maths in class, we often round it to 10. Keep both numbers handy. Example 6.4. Let's use the law. A 5 Newton force acts on a 2 kilogram object. Acceleration equals force divided by mass, which is 5 divided by 2, giving 2.5 meters per second squared. See how easily the formula gives the answer? Example 6.5. 2 steps this time. A 10 Newton force on a 5 kilogram object gives acceleration equal to 10 divided by 5, which is 2 meters per second squared. Starting from rest for 4 seconds, velocity equals acceleration times time, that is 2 times 4, giving 8 meters per second. Force gives acceleration. Acceleration builds up speed. Example 6.6. Setup. A little puzzle. A constant force gives a 5 kilogram object an acceleration of 2 meters per second squared. Now, what force would give a 3 kilogram object the very same acceleration? Let's work it out. Example 6.6 solution. The acceleration is the same, so just use F equals ma with the new mass. 3 times 2, giving 6 newtons. Neat! Once you know the acceleration, finding the force for any mass is easy. Pause and ponder. Same force, 2 masses. Ponder this. If the same force acts on a light object and a heavy object, do they accelerate equally? No, the lighter one speeds up more. Same force, different accelerations. Pause and ponder. Direction of acceleration. And which way does the acceleration point? Always in the direction of the net force. Push forward, it accelerates forward. Push back, it slows. Force and acceleration always share a direction. Transition to third law. So far, we've watched a single object respond to forces. But forces come from somewhere, from other objects. The third law turns our attention to what happens between two objects. Get ready for something surprising. Forces occur in pairs. Here's the big idea. You can never have a lonely force. Every force is one side of an interaction between two objects. Forces always come in pairs, never alone. Action and reaction. When object A pushes on object B, the action, object B pushes right back on A, the reaction. These two are equal in size and opposite in direction. Push the wall pushes you. Third law statement. And so the famous line, to every action there is an equal and opposite reaction. Short, memorable, and one of the most quoted sentences in all of physics. Say it once and never forget it.
Good morning, students. Today, we begin an exciting journey into the fascinating world of forces and motion. Every object around us moves because of stop motion, forces change speed, or even change direction. From a simple push on a ball to the launch at how forces affect motion. Let's explore the science that moves our world. Students, inertia is not just a scientific idea. We experience it every day in our lives. When body remains in its state of motion, this resistance is called inertia. Objects at rest resist starting to move. And moving mass of an object, the grain knob resists stopping. Inertia explains why objects prefer to keep doing what they are already doing. Students, Newton's first law explains what happens when there is no net force. But what happens when a net force causes an object to accelerate? The greater the force, the greater the acceleration produced. But when mass increases, acceleration decreases. This powerful second law helps that force us understand motion throughout the entire universe. Students, let's see how Newton's second law works in real life. When a small force is applied, the ball gains only a larger force to larger acceleration. When the mass increases, acceleration decreases for the same force. From force, mass, and acceleration are direct through even rockets. Newton's second law explains how objects accelerate. Students, now that we understand Newton's second law, let's learn about the unit used to measure force. This force that accelerates 1 kilogram of mass at 1 meter per second, we call it 1 Newton. Students, now that we understand Newton's second law, let's learn about the unit used to measure force. Imagine an object with a mass of 1 kilogram at 1 meter per second. The force required to produce this gravitation wettings in an oblong Newton kilogram. In every force we measure, holding a small 100-gram object in your hand, roughly via rocket launch, is expressed in newtons. Students, have you ever wondered why objects always fall towards the Earth when dropped? This happens because Earth's gravitational force that pulls objects towards the center of the Earth. The gravitational force acting on an object is called its weight and is calculated using F equals mg. Gravity gives objects their weight and keeps us firmly connected to our planet. Students, have you noticed how cricketers pull their hands fastball? This move increases the time taken to stop the ball. When the stopping time reaches, the accelerate increases. According to Newton's second law, the smaller exudes a smaller force. That is why pulling this backward and makes catching safer. Even professional sports depend on Newton's laws of motion.
Class 9 and 10 students, don't worry, make science and social science easy with your CBSE teacher. Subscribe now, like, comment, and press the bell.